Okay, good morning everyone. Welcome to PPT. Today we are going to discuss the topic chaos in discrete memester based system with fractional order differences. Before going to or talk about the topic, let me introduce myself. Myself Bhuvaneshwar from CSCA section. You can see my roll number on the screen. This is my topic chaos in discrete memester based system with fractional difference. Like this whole PPT is belong to the subject discrete mathematical structure. Okay, without any further delay, let me move into the PPT. Okay, you can see on my screen the table of content which I am going to discuss in the whole PPT. This is going to, like this is going to be in my PPT. Like the topic chaos in the discrete memester based systems fractional differences. This is going to be content. First introduction. I will first introduce you what about the topic and what the prerequisites of the topic, and later I am going to discuss the discrete memester based chaotic map of partial order difference. I'm going to do a brief description about this, and later I am going to discuss about the dynamic analysis, what I meant by dynamic analysis, and further, and later permutation entropy complexity analysis. I am going to discuss deeply about the permutation entropy complexity analysis. After this completion of this PPT, I hope you are going to answer many few questions based on this topic. Okay, let me clear the slide. Yeah, this is going to be our introduction, like prerequisite of the topic. To know more about the topic, so we require from prerequisites. These are the prerequisites of the topic. Let me let me discuss with you. Let me have me a pen. Yeah, fractional calculus is an important branch of mathematical analysis. It can describe the physical process more accurately, featuring the inherent properties of long-term memory and non-liquidative way significantly. Compared with the concept of continuous fractional order calculus, the studies on discrete fractional order difference is a new topic because the theory of fractional order difference be directly introduced the chaotic map to construct fractional order map, and the modeling and application of fractional order chaotic map has become an hot issue in recent years. Yeah, therefore it is an interesting to introduce the fractional order difference into an Amritsar based chaotic map with special behavior and Orman motivation to investigate the behavior of the amplifier of the transport of the chaotic fractional order difference form. Yeah, this is the introduction. Yeah, now before understanding the concept, let me derive some formula by using the theorems which we can further discuss the whole. In this section, the fractional order difference on Kaplan definition is introduced. Like, let me introduce the Kaplan definition of the fractional order difference. Define nt naught. We will define it with nt naught here. Like nt naught is equal to t naught comma t naught plus t1. Like, it's an arithmetic sequence which incrementing by 1 comma t naught belongs to R. It belongs to real numbers, the set of real numbers, and delta you can see the here the assumed equation as delta mu t is equal to mu of t plus 1 minus mu of t. This is the, like, we know the delta means change, right? Like, this is the change mu of t1 plus mu of t. This is the delta t. Let's define delta t as follow as equation 1, or let us consider it, no, it's not equation, just in basic situation, basic equation. Now let us see the definition 1 and the theorem. Let me erase the screen. Yeah, let me take a pen. Definition 1, for mu, like mu labeled nt naught gives us to R the discrete fractional order v greater than 0. V does not belongs to n mu t is defined on n of t naught. The delta difference is given as in the equation 31 comma 32, and you can see the formula on my screen which describes, like, delta mu t naught mu t is equal to 1 by gamma of m minus v, which into summation of s stands to t0 t minus mv into t minus sigma s whole power m minus v minus 1 into delta power m mu of s. This is the basic formula which given here. T belongs to n of t naught plus m minus b. This is the definition which we got for the formula, where t naught is the start point and gamma v is the gamma function. Like, this is a gamma function, gamma of v, like you can consider the gamma function gamma of v equal to integration of 0 to plus positive infinity. Like, consider the limits from 0 to positive infinity. E of v minus 1 into e of minus t delta t into sigma of s gives rise to s plus 1, and m is equal to v. V is a step function. T of v is an falling fractional which is defined by T of t power v is equal to gamma function of t plus 1 divided by gamma function of t plus 1 minus v. Yeah, these are going, let me erase. Erase. Yeah, yeah. um, yeah, this is going to be a consider it as an first equation which we did right now. Consider it as an second equation which we did right now, as I marked on the screen. First equation and second equation. Let me erase it. Yeah. Now again we discuss theorem. We are going to discuss another theorem here. Theorem 1 for the delta fractional order difference equation. Let me wait. Yeah. Yeah, for the delta fractional difference equation, this is going to be equation as similar as before, but in place of t we are going to consider s. In place of s we are going to consider c of delta power v t naught mu t is equal to fractional of t plus v minus 1 mu of t plus t minus 1, whereas delta t naught is equal to mu k is equal to 0 comma 1 comma up to m minus 1. Then the equivalent discrete integral equation is obtained as mu of t is equal to summation of k is equal to 0 to m minus 1 t minus t naught whole power k by k factorial into delta k mu naught plus 1 by gamma of v summation of s equal to t naught plus m minus v up to t minus v into t minus minus v. This is the equation which we got. Into this is the equation which we got. From the equation 4, it shows that the long-term memory effects of the fractional order system, the current state depends on all the past states, while when the fractional order v is equal to 1, the system disintegrates into the integral order system and no longer has the memory effect. You can see the coplanar graph for this. This is going to be your graph like this. Take x-axis I power n, y-axis of v of n, and plot the graph. Then you can get an this kind of shape, like combination of you can get basically it's look like a graph wave where the graphs are plotted from this variations. Omega is equal to 4 into 10 power 1. Like first red line indicates, let me erase. Yeah, red line indicates for omega is 4 into 10 power 4. Blah, 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 blah. Okay. Yeah, now uh, now let us see the discrete memester based chaotic map on fractional order difference. Here the fractional order difference theory is introduced to the discrete mathematical based chaotic map because the chaotic map has two components, three components of fractional order chaotic map and an obtained one. Both the system and memester are fractional order. The system is fractional order and memester is an integrated order. The system is integrated order and the memester is fractional order. Let us reduce the equation of Fs first. The differential equation obtained is delta xn is equal to xn minus 1 minus k of xn minus 1 cos y of n minus 1 minus x of n minus is equal to minus k x of n minus 1 cos y of n minus 1. This is the delta x1 equation. As you can see, delta y1 is equal to y of n minus 1 plus e of xn minus 1 plus y of n minus 1 is equal to e of xn minus 1. This is going to be delta xn delta y formulas. By introducing the Chapter difference operator, the Fm is written into the equivalent discrete integral form as xn is equal to x naught plus 1 by gamma of v summation of t minus v by x is equal to t naught plus m minus v t minus s minus 1 whole power v minus 1 the whole bracket minus k x s plus v minus 1 cos of y of x plus v minus 1, where yn is equal to y naught plus 1 by gamma v summation of s is equal to t naught plus m minus v up to t minus v t minus s minus 1 whole power v minus 1. Well, this is going to be parallel graph for that, as you can see on my screen. The discrete memester based chaotic map on the fractional order difference. This is s. Let us assume s is equal to s plus v is equal to j. Then the numerical equation of fm is reduced by xn is equal to, this is going to the first equation. Then this is the second. Similarly, the equation of s is obtained by, these are going to be the second equation for this. Like consider this as an 10th equation, this as an 11th equation, this as 12th. And if you parallelly plot the graph for this, then it's going to be the parallelly plotted graph for this, where from mu to load of area. Now we are going to discuss about the dynamic analysis. In this section, dynamic behavior of FSM, FSI, and IFs are analyzed and numerically simulated respectively. Here, the semi-parameters fixed is equal to 1 into 10 power minus 4, and initial values are set to x of y is equal to y of n is equal to 0 minus 1. Now here we are analyzing the bifurcation versus maximum Lebrun exponent MLE of FS FM with fractional order mu is equal to 0.85 and variable system parameter k are plotted in figure 3.a and b respectively. Like these are going to be pictures a and b plotted here for bifurcation versus maximum Lebrun exponent. These are going to be the two graphs for that. Now, the two subfigures illustrate the FSM explits Chavos behavior in K belongs to 2.49. Like these are going to be boundaries union. Like this is an closed boundary, this is an step boundary. Like you can, these are the boundaries which were plotted for the graph. It should be noted that the MLE value between the two black slash line K belongs to 2.352 has a slight formulation around the value 0. Again. Dynamic. Although the bifurcation diagram corresponding to this fabrication internal seems to be chaotic, the system is in quasi-periodic state. For example, where k is equal to 2.4, the sequence its corresponding attract phase diagram are given in figure 3c and d respectively. It showed that attractor of this system is two circular rings, which proves quasi-periodic state of the FSM, while the system parameter k 2.7 and the illustrate the chaos behavior of SFFM. These are going to be to show that illustrate the chaos behavior of SFM systems. Yeah, but now let us discuss the permutation entropy complexities analysis. In this slide, from now we are going to discuss about the permutation entropy complexity analysis. Complexity algorithms of a non-linear system is an indicate of Tromir how closely time sequence approaches to random sequence. For chaotic system, the higher the complexity is, the higher the randomness of the pseudo-random sequence generated by the chaotic system it is. So it is more conducted to be applied to chaotic ensure the communication. For calculating the complexities of an procedure function order chaotic maps, a famous complexity algorithm they called permutation entropy P complexity is introduced, embedding dimensions m and time delay gamma and the parameters P complexity algorithms. Here the are set to m is equal to 5 and gamma is equal to 1. Now permutation entropy complexity analysis. P complexity with the different parameters k and v of FSFM, FSIM and ISFM are given in figure. The darker color means the complexity of an generator sequence of higher, and the white area indicates the system has bounded behavior of single fixed point from this. Like you can see the graph and you can compare the color and you can find the complexity with different parameters of k and v of FSM, FM and FSIFM and ISF and FM. You can compare the colors of each and every graph here which was presented over in the slides, and you can plot the graphs with different parameters of FSFM, FSIM, ISFM. Like then you can arrive at the final conclusion of the given required equations. Now these all are good. Like now still now I have introduced all topics related to the topic. Now let me conclude the topic. The Capno fractional order difference has initially a second order discrete mathematics based map. The free fractional order system models are obtained. Fractional order system equivalent and fractional order memorization fractional order system equilateral integrator order memester which is known as FSIM. Fractional order system equational integrator of a memester ISFM. The numerical stimulation lead to the following result. This numerical excuse me, like the numerical stimulation led to the unfortunate results. A three kind of fractional order system show different complex dynamics behavior, and all the system have quasi periodic stable form entering the chaos. Again, the complexity these are the following results. The complexity sequence generated by the system increased with the decrease of fractional order. The dynamic behavior of the system is affected by initial values, which leads to the appearance of the coexisting attractions. And in the discrete fractional order memester, the lobe area of this loop decreases with the decreased fractional order. The result shown the discrete fractional order memester is worthy of further study and can be applied in mathematical operation or secure communication. The next work will be considered in stability and analysis of the fractional order memester and try to apply the synchronization control. Yeah, this is the conclusion. Let me again briefly recapitulate what still I said. Let's start. We discussed the introduction for fractional calculus, and I given a basic definition in equation one. Like you can see on my screen, I gave the equations for the definitions here, fractional order. Again, later we have discussed this theorem, and we arrived at the formula, and we explained the graph with different parameters. And then we came here at the discrete mathematical order difference, and we derived this equation, and like we explained this equation 8 equation, and we explained about this graph. And later we saw this equation, later we saw the equation 10, 11, 12, and the relation between these equations with respect to this graph. And later we came to the dynamic analysis, how fractional order are FSIM, ISFM are analysis, the dynamic analysis. And later we plotted the graphs with different parameters of bifurcation and maximum Lyapunov exponent, which you shortly call as MLE and FSFM. These are going to be result here. And later again we discuss this related. Yeah, sorry for the interruption. Yeah, again we got these slides here, and we discussed this different plots here. And again we discussed the permutation entropy, the complexities and everything, complexities and everything here. And again we talked the different relations of FSFM, FSMI, FN, the graphs plotted with these two, and we discussed that how variation of this with the different color of the changing of the graphs. And at last we came to the conclusion of the topic here. Yeah, this is my PPT. Thank you. This is the I hope I explained everything about the topic. Thank you.